Hello, with this video I would like to begin Chapter 7 on atomic structure and periodicity. The goal of this unit is to understand the electronic structure of atoms. We know that atoms are made up of protons, neutrons, and electrons. The big question is, how are the electrons in the atom arranged? Well, you might ask, why do we care? Well, that's a really complicated question, but the simplest answer is chemical bonding. We know that chemical bonds form when atoms gain, lose, or share electrons. The arrangement of electrons in the atom is going to completely determine how atoms gain, lose, and share electrons. So we'll begin by talking about electromagnetic radiation. What is electromagnetic radiation? Well, essentially, it is how energy is transmitted through space. If I want to send energy from one point to another point, I'm going to do so with a beam of electromagnetic radiation. And it's important to understand that electromagnetic radiation is a wave-like phenomenon. If you study electricity and magnetism in advanced physics courses, you'll learn that EM radiation is basically made up of oscillating magnetic and electric fields that travel through space that are perpendicular to one another. We don't particularly care about that. All that we want to know is that, like any wave-like phenomenon, it is characterized by a wavelength, the distance between two peaks, the frequency, the number of peaks that cross a fixed point in a given time unit, and the velocity. And let's look at how these are related to each other. Here's an example of a wave traveling for 1 second. Lambda 1 shows the wavelength, the distance from peak to peak, and the frequency is 4 cycles per second, or 4 hertz. Now, if I were to shorten the wavelength from lambda 1 to lambda 2, in fact, shrink it by 1/2, I see that the frequency increases from 4 cycles per second to 8, and likewise, I can go even further. That tells us the relationship between wavelength and frequency. They are, in fact, inversely proportional. We saw in the previous slide that as the wavelength gets shorter, the frequency gets bigger, as long as the velocity is being held constant. Now, you all recall from your first year of chemistry that if two variables are inversely proportional, they multiply to give a constant, and that constant, in fact, is the speed of electromagnetic radiation. The equation we use, which I hope will look familiar to you, is C equals lambda times nu. Lambda is the wavelength of electromagnetic radiation in meters. Nu, the Greek symbol nu, is the frequency in units of reciprocal seconds, or if you prefer hertz. If hertz confuses you, you can simply use 1/seconds. And C is the speed of electromagnetic radiation in a vacuum, which has a value of 2.998 times 10 to the 8th meters per second. The type of electromagnetic radiation is based on the wavelength and frequency, and pretty much every physical science textbook ever published, at least in the 20th century, has a diagram that looks like this, the electromagnetic spectrum. On the spectrum, wavelength is increasing from left to right, and you can see all different sorts of electromagnetic radiation. Radio waves have very long wavelengths on the order of thousands to tens of thousands of meters, whereas gamma rays have very short wavelengths on the order of 10 to the negative 12 meters. As you can see, visible light that we can perceive with our eyes has a very narrow range between about 4 and 7 times 10 to the negative 7th meters, or using a unit that's a little bit more common, between 400 nanometers at the violet end and about 700 nanometers at the red end. Okay? And of course, at shorter wavelength than violet is ultraviolet, and at longer wavelength than red is infrared. Now, all was fine and dandy up until the very end of the 19th, very early part of the 20th century, when scientists made some discoveries that really confused them. They thought electromagnetic radiation was simply a wave-like phenomenon, but a variety of different experiments showed that electromagnetic radiation, under certain circumstances, can be particle-like. That is, when electromagnetic radiation is absorbed or emitted by matter, it is done so in chunks or discrete amounts. And actually, we use the term quantized to refer to that phenomenon. Okay? To say that electromagnetic radiation is quantized means that it is absorbed in discrete amounts, and that chunk, the term that we use to describe a particle of electromagnetic radiation, is a photon. And we say that a photon contains a quantum of energy. To calculate that amount, we use the equation delta E, the amount of energy gained or lost by an atom when it absorbs or emits a photon, is equal to n times Planck's constant times the frequency, or by rearranging and substituting in place of frequency speed over wavelength, n times h Planck's constant times c divided by lambda. Okay? N is the number of photons emitted or absorbed. Usually that's just one because we're talking about a single absorption or emission. H, Planck's constant, has the numerical value and unit given there. You don't have to memorize that. It's always given to you. Nu is the frequency in reciprocal seconds or hertz. C is the speed of electromagnetic radiation. And lambda is the wavelength in meters. Okay? And as we see, the energy of the electromagnetic radiation is directly proportional to frequency, whereas the energy is inversely proportional to the wavelength. So as the frequency goes up, the energy contained in a quantum of electromagnetic radiation increases, but as the wavelength increases, the energy decreases. So obviously the first skill is to interconvert between energy and frequency. So let's do a problem in which we do that. Microwave radiation has a wavelength in the order of 1 centimeter. Calculate the frequency and energy of a single photon of this type of radiation, and calculate the energy of an Avogadro's number of photons, called an Einstein, of this radiation. If you'd like to pause the video and try this yourself, please do so, but I'll continue. So we're given the fact that the wavelength is 1.0 centimeters, which is 1.0 times 10 to the negative second meters. I'll start with wavelength times frequency equals speed. To calculate frequency, I will divide both sides by wavelength. What's new? C over lambda. And I'll plug in 2.998 times 10 to the 8th meters per second, divided by the wavelength of 1.0 times 10 to the negative second meters, and that gives me a value of 3.0 times 10 to the negative 10th, 10 to the positive 10th, not negative 10th, 10 to the positive 10th, units of reciprocal seconds as my frequency. To calculate the energy, I will simply use energy equals Planck's constant times frequency, and that gives me 6.626 times 10 to the negative 34th joules times seconds times 3.0 times 10 to the 10th hertz, or reciprocal seconds, or an energy of 2.0 times 10 to the negative 23rd joules. And I'm just going to put in a joule per photon because we're assuming that we're dealing with a single photon. Okay? Now, if we want to calculate the energy contained in a mole of photons, well, we need to use Avogadro's number. So that would be equal to 2.0 times 10 to the negative 23rd joules per photon times 6.022 times 10 to the 23rd photons per mole, or 12 joules per mole as my energy. Okay? So if I absorb 1 mole of microwave photons, I'm absorbing 12 joules of energy. Put boxes around my final answers there. Okay, let's do one more example. The work function of an element is the energy required to remove an electron from the surface of a solid element. Okay? The work function for lithium is 279.7 kilojoules per mole. That is, if I want to remove 1 mole of electrons from 1 mole of lithium atoms to the surface, I have to add 279.7 kilojoules of energy. Okay? What is the maximum wavelength of light that can remove an electron from the surface of lithium? Well, let's do a little roadmap here. I am given the energy in units of kilojoules per mole of photons. It seems like I probably want to convert that to energy in units of joules per photon, because if I know how much energy is in 1 photon capable of kicking an electron off, then I can simply use the equations we saw before to calculate the wavelength. So the first calculation is pretty much just unit conversion. So I'll start with my 279.7 kilojoules per mole of photons. We'll want to convert that to joules first, times 1,000 joules per kilojoule. And then to convert that from joules per mole to joules per photon, I will divide by Avogadro's number, or multiply by 1 mole over 6.022 times 10 to the 23rd photons, to give me an energy of 4.645 times 10 to the negative 19th joules per photon. Finally, to calculate the maximum wavelength, and again, maximum wavelength because minimum energy, remember wavelength and energy are inversely proportional, I will use my rearranged equation. Wavelength equals Planck's constant times the speed of electromagnetic radiation over energy. 6.626 times 10 to the negative 34th joule seconds times 2.998 times 10 to the 8th meters per second divided by the energy I just calculated, 4.645 times 10 to the 19th joules, and that gives me a wavelength of 427.7 nanometers, which happens to be blue light, hence the blue box. Okay, so visible light that has a wavelength no bigger than 427.7 nanometers has enough energy to remove an electron from a lithium atom at the surface of lithium metal. Now, section 7.2 is on the nature of matter, and we are largely going to skip this because much of the stuff contained in this section, primarily on the de Broglie wavelength of matter waves, is not part of the AP curriculum. Unfortunate because it's fairly interesting. So I'll just cut to the chase so you know what the summary is. Okay? Just as there is a wave-particle duality of energy, energy can either be wave-like as it's traveling through space, or particle-like as it's being absorbed or emitted by matter, there is also a wave-particle duality of matter, which means that all matter exhibits both wave-like and particle-like properties. Large chunks of matter, like a baseball for example, are mostly particle-like. You can actually calculate the wavelength of a baseball if you know its mass and velocity, but it is many, many orders of magnitude smaller than the size of a nucleus, so you cannot even observe it. Couldn't figure out why the baseball kept getting bigger. Then it hit me. Small bits of matter, like photons, and photon is not matter per se, but it can behave like matter, have mostly wave-like properties, but they do have some particle-like properties, whereas intermediate sizes like electrons have both. Electrons are particle-like in that they have mass, but they're wave-like when they travel through space. Okay? Experiments show that a beam of electrons has wavelength and frequency and does everything else the waves can do, and that will have important significance in upcoming sections. And that's pretty much all.